Hey, that sounded cool, didn't it? Well, you know what else sounds cool? Exponents. And that's exactly what we've got in store for this unit. So we're starting off unit 7, which is dealing with exponents and all the different rules with exponents, different types of exponents, different applications of exponents. And so I want to start off with this first section on zero and negative exponents. Um, remember, exponents are those little numbers up to the top right of a different number of the base, and it tells you how many times to multiply that base number by itself. So there are times when we might have a zero or a negative exponent. So let's look at this little example here to get ready for this unit. We could fill in the blanks with all these different spots over to the right. Like if we have 2 raised to a certain power, 2 to the fourth I believe is 16, 2 to the third is 8, 2 to the second is 4, 2 to the first is 2. All right, keep going with that pattern. It looks like we're dividing by 2 every time because that base is 2. Um, and 2 divided by 2 would be 1. 2 to the 0 power is 1 then. Let's just keep going. Divided by 2, it'd be 1 over 2. Divided by 2, that by 2 would be 1/4. So we're going to stop right there. How about tens? 10 to the fourth would be 10 with 4 zeros. 10 to the third would be 1,000, so 3 zeros. 10 to the second would be 100. 10 to the first is 10. Looks like we're dividing by 10 every time. So then 10 divided by 10 to keep with this pattern would be 1. So now we have 10 to the 0 power. That's also 1. Interesting. Divided by 10 would be 1/10. Divide that by 10 would be, oh, sorry, no. Divide that by 10 would be 1/100th. So let's see if there's a way. We're going to see if there's any patterns, if there's any specific things or rules that we know about these zero or negative exponents. And that's what our goal is going to be focused around. Our objective is to simplify expressions involving zero and negative exponents. So let's start off with a couple of properties. This first one is about 0 as an exponent. So here is the rule. For every non-zero number a to the 0 power is equal to 1. In other words, anything to the 0 power equals 1. So here's 3 examples. 4 to the 0 power is equal to 1. Negative 3, if that whole thing is raised to the 0 power, is equal to 1. 5.14 to the 0 power is equal to 1. Anything, any number raised to a 0 power is just equal to 1. Alright, how about negative exponents? Here's the rule for negative exponents. For every non-zero number a, an integer n, or a to the negative n would be equal to 1 over a to the positive n. So in other words, here's a couple examples. If we have 7 raised to the negative third power, to make that a positive exponent, we just put 1 over 7 to the positive third power. And then we can reduce that. 7 to the positive third, I think, is like 243. So this would be 1 over 243. Okay? Another example, we have negative 5 raised to the negative second power. Maybe you could have guessed it. To make it a positive um, power of 2, we just put this negative 5 raised to the power of 2 on the bottom, and 1 goes on top because there's nothing else there. All right, and that's all we have for those. So, negative exponents basically mean to change it to the reciprocal, and that would make the exponent a positive. All right, here's something to note. Um, why can't you use 0 as a base with 0 exponents? So you can't, like 0, um, 0, whoops, 0 to the 0 power is not equal to 1. Okay, we're going to look at a pattern. The first property on the previous page seems like this would be equal to 1, but it's actually not. So if we look at it, 3 to the 0 power is 1. 2 to the 0 power is 1. 1 to the 0 power is 1. Shouldn't 0 to the 0 power be 1? Well, let's look at it this way. 0 to the power of 3 is 0. 0 to the power of 2 is 0. 0 to the power of 1 is 0. So why would 0 to the power of 0 be anything but 0, looking at that pattern? All right, so it is equal to 0. So it's not possible for it to both be 1 and 0. Therefore, actually we're going to say it's undefined. 0 to the 0th power is one of those undefined terms. So why can't you use 0 as a base with a negative exponent? Because then you would have to flip it and put 0 on the bottom. You can't divide something by 0. That would be undefined as well. Alright, so let's do some examples with 0 and positive exponents, or 0 and negative exponents. This first one, 9 to the negative second power. Whoa. Here we go. It says, what is the simplified form? Well, remember, to make it a positive, we just make the reciprocal. So it'd be 1 over, 1 over 9 to the second power, which is equal to 1 over 81. Negative 3.6 to the 0 power. Well, remember, anything to the 0 power is equal to 0. So, or sorry, equal to 1. I made the mistake there. So, that raised to the 0 power is equal to 1 as well. So I'd like you to pause it and try at least a couple of these A through E problems. I bet you could do them all pretty quickly as well. And after you unpause it, I'll have the answers there for you. Alrighty, so here are all the answers for each of those 5. B might have been the easiest one because anything to the 0 power is 1. But the rest of them, we're just taking the reciprocal of each of them and then making the exponent a positive. And then we can simplify from there. So that's how I got those answers. Next example. This is still called a monomial because there's just a bunch of these exponents multiplied together. But we're going to start simplifying some of these. Here's another one. I think I have a couple other ones here. So let's take a look at this one. We have 5a to the third and b to the negative second. You might say, what's wrong with that? Well, there's a negative exponent. So the only thing we can change here is we're going to leave 5a to the third on the top because those don't have negative exponents. I'm going to put b and raise it to the second power on the bottom. And that would be the simplified version of that expression. We're going to do the same thing with b. The thing about b is the x to the negative fifth is on the bottom already. So again, then we just flip it to the top. Do the reciprocal. So it's going to be, it's going to be x to the positive 5 fifth power over 1, or just x to the fifth power, or 1x to the fifth power. All right? So likewise, I have 5 more examples for you. I'm going to ask you to pause it and try at least a couple of them, and then I'll show you the answers to those in a second. All right, so there you go. Those are the results, the answers for those. Take note of them. If you're stuck on one of them, make sure you ask next time you see a teacher. We're going to move on to a couple more challenging ones. This one right here, these are dealing with evaluating exponential expressions, so similar to what we just did, only now we have values for s. So I would say there's 2 different ways to do it. You could either plug them in first, or simplify it first and then plug it in. So let's plug them in first for this one. We could say 3 times 2 cubed times negative 3 to the negative second power. Okay? Now, if I take that, it's going to be 3 times 2 cubed, in other words, 3 times 8, over negative 3 squared. To make that positive, I have to put it on the opposite spot. So simplifying, it'd be 3 times 2 cubed is 8, over negative 3 times negative 3 is 9, and that would be 24 ninths. I'm going to leave it as that. You can make it into a mixed number or decimal, but I'm okay with that. So the other way would be to take 3s cubed t to the negative second and simplify it first. So that would be equal to 3s cubed t to the positive second. And then plug in. So when I plug in, I'll have 3 times 2 to the third power over negative 3 raised to the second power. And you end up getting the same thing. Same as before, this will be 24 ninths. So two different ways to do the same problem, pretty similar, but slightly different. So that is totally your choice as to which one you want to do, whether you simplify first, or and then plug in, or plug in and then simplify. So here's a couple more you can try. I will show the answers for those in just a second. All right, so there you have all the answers. Feel free to pause and look at them. What I did was simplify them first and then plug in, and that's how I got all my results. So one last thing here, I want to look at this one right here. It is an application problem dealing with bacteria. So let's read it through. A population of marine bacteria doubles every hour under controlled laboratory conditions. The number of bacteria is modeled by the expression 1,000 times 2 to the h power, where h is the number of hours after a scientist measures the population size. Evaluate the expression for h equals 0 and for h equals negative 3. What does each value of the expression represent in the situation? So let's do h equals 0 and h equals negative 3. So for h equals 0, it'd be 1,000 times 2 to the 0 power. 2 to the 0 power is 1, so that's just going to be 1,000 times 1, which is equal to 1,000. Okay? Now, if h is negative 3, we have 1,000 times 2 to the negative third power, which would be equal to 1,000 over 2 to the positive third power, which is equal to 1,000 divided by 8, which is approximately, I believe it's 125. Okay? Now let's think about this. The number of bacteria is modeled by that. So the number of bacteria after 0 hours is still 1,000. That makes sense to me. That means it starts at 1,000. The number of hours, how can the number of hours be negative 3? I'm wondering. Well, that just means that 3 hours before it was measured by the scientist, you can calculate, using that negative 3 as the exponent, you can calculate how many bacteria there were 3 hours earlier, and it was 125 bacteria only. So that's a real situation where exponential functions, exponents like this, are used, and there's a lot more where that came from for the rest of this chapter. So let's go back to our original goal and think about if we learned it or not. The goal is to simplify expressions involving zero and negative exponents. I hope you were able to do that. Um, and I hope you learned something in this first section of Chapter 7. Have a great rest of your day.